Welcome to Lecture Online. Now we're going to do a new series on first order differential equations. In this case, we're going to involve doing first order differential equations for which we need an integrating factor to find the solution. Now, what we're going to do here is start out with an exact equation, and then we're going to show you when the equation is not exact, you'll need what we call an integrating factor. So here's an equation that is an exact differential equation. The left side is a particular form. We'll show in just a moment why that is. And so let's rewrite this because y prime can be written as dy dx. So we can say that this is 3x squared minus 2y squared plus the quantity 1 minus 4xy times dy dx. And that's equal to 0. Now, if we multiply both sides by dx, we'll get in the exact form that we're looking for. So multiply both sides by dx, we get the left side to be the quantity 3x squared minus 2y squared times dx plus the quantity 1 minus 4xy times dy is equal to 0. So now what that means is we have this equation in a particular format. If the left side is represented by the following equation, if this can now be written as du is equal to, and that would then be the partial derivative of u with respect to x times dx plus the partial of u with respect to y times dy. And then if we say that this is really represented by this equation right here, or at least the left side is represented by this, so then we can say that this whole left side of the equation right here can simply be written as du is equal to 0. And then if we integrate that, we get u is equal to, and of course u would be a function of x and y, it would have to be a function of x and y, is equal to some constant. Now what that means is if this is indeed the case, if this is equal to the equation of this format, then we can say this portion right here is equal to the partial of u with respect to x. This portion right here is equal to partial of u with respect to y. And then we can write this equation as m times dx plus n times dy is equal to 0, where m is equal to the partial of u with respect to x, and n is equal to the partial of u with respect to y. And then, if this is an exact equation, under these conditions, this should be an exact equation. If it's an exact equation, we can then solve for u, and then we can find a solution to this first order differential equation. So what that means is, if m is the partial of u with respect to x, and n is the partial of u with respect to y, if we now take the partial of m with respect to y and the partial of n with respect to x, then they should be equal to one another. In other words, the partial of m with respect to y should equal the partial of n with respect to x, because then what you can see is that the partial of m with respect to y is really the partial of u with respect to x and respect to y, and the partial of n with respect to x is equal to the partial of u with respect to y and respect to x, so therefore they must be equal to each other. And if they're equal to each other, then the equation is exact and we have a solution, or at least we can find a solution for it. What we're going to see in this series then, if it's not an exact equation, then we have to use an integrating factor to make it exact so we can find the solution. So quickly, to show you that this is an exact equation, we're going to take m, which is this quantity right here, and n, which is this quantity right here, take the partial with respect to y, take the partial with respect to x, and we'll show you that they're equal to each other. So the partial of m with respect to y is the same as the partial with respect to y of this quantity right here, which is equal to 3x squared minus 2y squared. Let's go ahead and do that real quick. So this is equal to, since x is a constant in this case, only y is the variable, then this would become minus 4y. And then if we take the partial of n with respect to x, this is equal to the partial with respect to x of the quantity right here, 1 minus 4xy. So this is equal to, remember in this case, y is a constant, only x is a variable, and so in this case, that would be minus 4y. And notice that these are equal to each other, so therefore we can say this is an exact equation. And then if it's an exact equation, well, we'll solve it as follows. What we can say then is we can go back over here and notice that this relationship, we can use this relationship right here, and say that the partial of u is equal to m times the partial of x. And so therefore u would be equal to the integral of m times the partial of x plus some function of y. Because in this case we know that y is a constant, so we know that y is a constant in this case, and so we know that we can end up with some function of y because y in this case is a constant. So m in this case is equal to this quantity right here, so this would be the integral of 3x squared minus 2y squared. With respect to x only, that means in this case y is a constant. Well, so we're going to have some function of y. If we take the integral of that, we get the following. We get u is equal to, that would be 3x, that would be, since it's with respect to x, it would be 3x cubed over 3 minus 2y squared x, because of course minus 2y squared would be constant, and that would be plus some function of y. Of course, the 3's cancel out, so it leaves us with u equals x cubed minus 2y squared x plus some function of y. Now we can do the same with the other relationship. We can do the same with this relationship. We can also solve for u, and the reason I want to do that is because I don't know yet what f of y is equal to, so I'm going to do it again with this relationship. Say that u is equal to the integral of n times the partial of y plus some function of x, because in this case we know that x is going to be a constant, like so. Then we plug in what n is equal to. Remember, n was this quantity right here, so 1 minus 4xy, so this is equal to the integral of 1 minus 4xy with respect to y being the variable plus some function of x. And so this would be equal to, integrate this, you get y minus, so we get 4xy squared over 2 minus 4xy squared over 2 plus some function of x. Of course, this and this cancels out, so we get y minus 2xy squared plus f of x. And of course, this is also equal to u. And then if we set these two equal to each other, because they must be equal to each other, then we get x cubed minus 2y squared plus some function of y must equal y minus, that would be 2xy squared. Ooh, I'm missing something here. Here, I forgot my x. I didn't copy my x down over here, so otherwise that cannot be equal. So because I have minus 2xy squared here, plus some function of x. Notice that this here is equal to that. On the left side I have an x cubed, on the right side I have a function of x. On the right side I have a y, and the left side I have a function of y, which means that the function of y is equal to y, and the function of x is equal to x cubed. So therefore my solution then is that u is equal to x cubed minus 2xy squared, and this function of y has to be equal to y, so it would be plus y. So this is then the function u, of which the du is equal to my differential equation. And since I know that u is equal to a constant, I can set this equal to a constant, and so therefore I can say that the solution can then be written that x cubed minus 2xy squared plus y must equal a constant, and therefore this is the solution to my original differential equation, because the differential equation I had here, this first order differential equation, was an exact equation because m and n, when I took the partial derivative of m with respect to y and the partial derivative of n with respect to x, they were equal to each other, which we checked right here. And when it's an exact differential equation, I can then solve for u, and then realizing that u is simply a constant, then I can find the solution to the differential equation. What we're going to do now in the rest of this series, we're going to show you equations that are not exact, and when they're not exact, we have to use an integrating factor to make it exact, and we'll show you how to do that. So even when this equation is not an exact equation, we can still find the solution by making it exact using the integrating factor. And this is what this series is all about.